So in the previous video, I mentioned briefly listed some four components that you want to know about the sampling distribution: the mean, the variance, and what happens when n is large, and what is the shape of the distribution. So let's think about them one by one. Here, the slides show the proof for the mean and variance, but I will skip that. The proof is not that important. The result is simple enough. So it's intuitive enough, simple enough, so you don't need to know the proof here in this course. So the result is that when you draw n number of observations at the same time and take their average, and the sample average, if you could repeat the sampling, on average, the expected value would be the mean of one single outcome, right? This is the true mean from a single observation, and this is the average of n observations. And if you take expectation, they are the same. Okay, it is simple. So the mean does not change, right? And so that means if you throw one coin, the probability of heads is 22%. If you throw 100 coins, the expected proportion of heads would be still 22%. No matter what, even if you throw 100 or 100 million coins, the proportion would not change, right? Or in our example, say suppose that you calculate the average the income from one person, or if you calculate the average income from 10 people, 100 people, or like a million people, basically the average does not change, right? As long as you are randomly choosing a person. However, what matters is the variance. When you throw one coin, the outcome is always 0 and 1, right? You cannot be closer to 22%. When you throw two coins, 0.51. So it cannot come closer to the true parameter. But as I said, when you throw 100 coins, if the true probability is 22%, your observation, your sample average can be different from 22%, right? When you throw 100 coins, it won't be 22, but it will be close enough to 22%, like maybe between 10 and like 30 something would be the most likely outcomes you can expect, right? So as the sample size increases, if you could throw like 1 billion coins at the same time, then the realizations will be almost correct as 22%, right? So then mathematically, it is represented here. The mean is the same, which is easy to understand, but the variance, the size of the random error decreases inversely proportional to the sample size. As you throw 100 coins, million coins, billion coins, then the error will be smaller. The deviation, size of the deviation will be smaller, become smaller, right? So this is a very important result because it captures the uncertainty or the size of the random error you have in estimation. So we usually take square root of that because we usually consider standard error. Standard deviation is square root of variance. So usually we use standard deviation of y bar, which will be square root of this guy. So as a result, will be proportional to 1 over square root n, not 1 over n. But the idea is the same. The point is it's decreasing. N increases, then the error decreases. And then, so mean and variance are simple. The results are simple. The results for mean and variance are simple. And then the other two things we would like to know. The third point is what happens when the sample size is infinity. That's the rule is called the law of large numbers. Law of large numbers, and simply speaking, the result is when n is large, variance goes to 0, but mean does not change. So I will talk about this more I'll focus on the variance to study what happens. And also, then what is the shape of the distribution? The answer is normal distribution. The shape of the distribution of y bar will be normal distribution by the center limit theorem. So all of these are actually very difficult mathematics, but the results are not that difficult. It is intuitive results, and it's natural. You can expect to see from like even coin tosses. So this is the slide, the textbook explanation of law of large numbers, but I'm going to skip that. It's not easy to explain the math. So let me try my own way. So we learned that the mean and the variance are given by this formula. So simply mean is constant, but variance goes to 0 as sample size goes to the infinity, right? As sample size increases, the variance will be, in the end, will be 0, which implies that there will be no random errors. So imagine variance is 0. So that means there is no randomness, no uncertainty in the limit. So if the sample size was actually infinity, then variance will be 0, and there is no uncertainty, no random errors, and which means y bar will be one number, no errors, it will be one number, but that number will be this guy because it does not change. The mean does not change, so if y bar was one number, then it should be this number, this value, right? So then it means that combining these two, combining constant mean and decreasing variance, you get the conclusion that in the limit y bar will equal to this guy with 100% always, for certainty. There is no randomness. So then in this case we say that y bar converges in probability to mu. So y bar, as n increases, uncertainty disappears and y bar will take this value for certainty. That's the how you can understand this sentence. It's not rigorous, not like mathematically super rigorous, but still it is the maybe best way to understand what it means. I remember I learned this convergence in probability when I took mathematical statistics as an undergrad student. At that time, I could not understand what it meant. I had no idea what's the difference between simple convergence and convergence in probability, and what is this notation. So I still remember the bad feeling and not understanding anything in the class. So I tried to avoid the notation, mathematical equations. So this explanation, what I'm doing here, should be fine, I believe. And notationally, we write it as y bar converges to mu y, this value, but we put p on top of the arrow to show that it is convergence in probability. So it means so if y bar was a constant, just non-random number, then you can just think about convergence, but here y bar is random variable, so you have to put p here for rigorous notation. And then suppose that you are estimating mu using the estimator y bar. So y bar is your estimator to guess mu. And suppose that y bar converges in probability to your parameter mu, which means the random error will disappear in the limit and your estimator will always equal to your true parameter in the limit. So that means your estimator will be perfect in the limit. Of course, you will never be in the limit, but it's desirable property. If you could go to the limit, then you will be perfect. Your estimation will be perfect. That's the meaning of this, and which is nice. So we say y bar is a consistent estimator for mu y. So consistency is an important property of an estimator. So it involves a little bit of complicated argument, mathematical argument. I try to explain that as simple as possible, as easily as possible. Consider variance shrinks to 0, but the mean equals to the same thing. So in the limit, no uncertainty equals to 1 point, and that point, the value is exactly what you wanted to know. So in the limit, it's perfect. That's the meaning of consistency. And the central limit theorem will be discussed in the next lecture. I think it becomes more complicated. I hope you follow this, and you will see those concepts later. So at this point, you may think or you may not understand what I'm saying, but later you will get more familiar with them, hopefully. Okay, thank you for watching, and see you in the next lecture.